to start this session, and it's my pleasure to introduce to you Professor Younes Messadeq. Professor Messadeq works here and also in Canada. So we say that he obeys sometimes he's a particle, sometimes he's a wave, so we don't know if he's here or in Canada, but now he's here. Now he's a particle. It's a pleasure to do this, Professor Messadeq. Thank you for being here. It's always a pleasure to have you here.
Okay, good morning, ladies and gentlemen. It's my great pleasure to be here again at home. In fact, I'm a little bit tired because this guy who went to the bar and we're turned back too late. Please forgive me if I give some words in French or in Portuguese. I didn't drink, I just drink some water. Maybe the effects of all this beer solvent in the air, this is. What I will try today first to speak about the optical fibers and high tech. It works. What I'll try today is to speak a little bit about the fundamental of optical fiber. Who have never get any courses on optical fiber? Please. Come on. Okay. Please forgive me for the students have already seen all the basic. I will give just the basic how it should look like optical fiber. What is how we can use it, and what is the historical of that. And this is something it's very interesting in the way just the optical fiber is coming from the people who dream. This is all the time I told my students, if you haven't any dream, forget it. We have a several dream in our life, and I think this is one point in science. You must have some challenge. What you are looking for the next century, what we are looking for the next century. If you are not in this point, please don't play football or tennis because you get more money. I don't think that we will have money doing science, but sometimes we can get some. Okay, which one? I will try to follow this part line. As I said in the beginning, introduction, I will give the chronology of optical fibers. What is the property of these fibers? Some few words about the mechanical property because it is one of the important points if we want to use these materials. What is the challenge? The challenge how to prepare a good optical fiber. As I said, everybody can make optical fiber, but as I said the word spaghetti, you can do it at your home. But it's unuseful because it hasn't the same property that we are looking for. And finally, I will speak some specific fibers and what is the next challenge. The first thing, we are chemists and we are in the Institute of Chemistry. If we want to prepare any materials, we must follow this strategy. First things, any material, we have the starting material, the components that we will be using first, and in this way we need to learn a little bit about the chemistry, the basic chemistry. The second point, the property of this material, and in this case we go to the physics, our colleagues in the way to help us to understand how it will be useful, this material. And at the end, what is the process that we'll be using in the way to focus what is the application that we are looking for. And this is very important. And all these three challenges, this is what I told, multidisciplinary things. And this is something that all the time we need to be broad our mind in the way if we want to develop any kind of new materials. Okay, I am sure that you learned a lot of bit about glasses. Lily confessed me yesterday that he is happy because I learned a lot of things about glass. Yeah, sure. Soldier process and everything. Besides all the time when I am discussing with the people who are told us that we are working in glass, yeah, glass is very easy. Because what you are doing all the time, we are cooking. Yes, we are cooking, but not so easy as it is. Because we have different process, as you can see in these figures, that allows us to prepare different kind of glass. And just I want to point here, depending of the state of the material that we are starting for, we can get different behaviors. And in this case, I will start what you have been doing in the experimental part. I think 2 days ago, you start from the melting your component at higher temperature, then you cool your system and you get the glass. This is what we call the quenching techniques. This is one point. The second point, we can start from the gaze phase. And in this case, I thought why I am looking for that. Because it's so important to go to phase, to vapor phase, in the way what we are looking for, what is the most important for that. And again, we can start from crystalline. And from that, depending the process that we are using, by radiation, we can shine with laser, or just by shock wave, we can get what we call amorphous state, which is different than glass, and then we can follow by a specific treatment to get the glass. And this is so important. I like this figure because really they give us a clear techniques in the way to show us, depending of what, remember my inspection in the beginning, what I am looking at the end. I'm looking for glass, which kind of glass I'm looking for, which kind of property I'm looking for. And if I am looking in the form of tentatives or in the form of the fiber. Today we will focus just for the fiber. And from that, we need to know which kind of process that we will use in the way to get a very high quality of the material of these fibers. And please, I go to these books because he gives all information about all the process of preparation regarding the glass materials. I hate the technology. Okay, I like this figure because this is something that gives us what is the history of preparing the materials. And this is one of the driving force for the technology that we have today, for the optical fiber that we have today. But I said all the time, imagine if you wake up one morning and you couldn't open your internet. You are frustrated. But imagine if we didn't get the optical fiber, what would be the world? And this is something that, because of one thing what we told, the optical losses of this material, and I am coming back to explain for the people who have never seen that, how we can do that in the lab, how we can prepare, and what is the important things for that. We can, if we don't discover the optical losses, dB per kilometer, I will explain later that, during the years, after the 16, we have a big change in the history. And this is an important point for us, and it was the driving force to get the internet today at our home. Okay, the second driving force, it was communication. During the whole history, you can go to the internet and you can see, as I put it here for this figure, you have all the historical communication in the telephone, from the first telephone in the world till 2008. What is the progress of the technology of that? But one point that I want to point here, what was the important point in the chemical or scientific point of view that changed our world in the 60s to now, to the internet. And this bridge, it was because of dreaming of some people, the things that someday we'll be able to get a higher bandwidth, a higher capacity of transmission in our life. And today, mainly in the last years, we are looking for higher and more higher for capacity. And also our children, they are looking for more and more capacity for transmission. And this is, I like this transparency because they show us all the evolution of the optical fiber communication or the chronology of that. The first thing that you never forget, and this is something that you can do it at your home, your friend, your sister, or your kids, just to show them some small experiment. What we told, this is the tunnel experiment in the 1878, when with your laser, $1, and you put it just here, water, and you can see the guiding light inside the water. This is something that we show in the school. I remember at our students go to the school to show the students to explain how light is guided inside any medium. It can be air, it can be liquids, or any kind of medium that we have. The second thing, the first dielectric analysis that show us it is possible really to make how these lights go inside the material. The earliest experiment with silica fiber coming in the 30s, and something that we forget all the time. That Capani in 51, he made some image, transmission of image using bundle fiber. Bundle fiber, what I mean, this is several fibers together, and he made a high resolution of image. This is something in his book in 51. Remember, we didn't yet discuss about all in the history or on the textbook. They start in the 66, and they forget the history that they have something, they have some in it, that some people was thinking, and they did some experiments before with optical fiber before the 60. Of course, in 61, Sneijder, he did the first experiment, mode analysis of optical fiber, when they show it is possible to make the first laser in 61. And again, at the same time, several groups, they made the first semiconductor lasers. This is very important, you can see. At the same years, the 60s, we had several driving forces that they allow us to get really this dream of to get the transmission through the optical fiber. It's a reality. And of course, in 63, DuPont, the company, they made the first optical fiber based in plastics. Sneijder in 64, again, he showed, analyzed the first fiber laser based in, I will show later, based in a silica fiber doped with neodymium, and he showed the first laser in one micron. And I put it here, this is our story starts from here. Our story starts from him because Cow and Hoffman in 66, he showed that it is possible one day he proposed that we can get a long distance of communication using some optical fibers. Of course, from that, Corning company showed it is possible already to reach that because they have been able to get losses of fiber around less than 20 dB per kilometer, and just 10 years later, we improve against the quality of these losses. We get 0.2 dB per kilometer at 1.50. And again, in the 18 other group at Southampton in England, he showed the possibility to make some fiber amplifier, and real maybe he will focus in this part. And again, the Austrian coming in 91, we're coming from a new generation of fiber. Called microstructure fiber. I will speak a little bit about this kind of fiber. And finally, in 96, we showed the first solid core fiber from the group of Russell. And finally, I will end with just a very nice example of technology development recently, 2007, when Corning the show we will be able to get a fiber without insensitive to bending. Insensitive to bending, I mean, I can very hard with a good mechanical property. And this is something new, and this is something that will change again the application for such materials. As I said, the story starts from the 60s. The 60s will start the revolution of telecommunication. We start with first, with Mayan, he showed it was possible to produce the first laser based on Aerobi. And the second thing, this guy, Sharkov, he showed it is possible, he is theoretical, and then they sometimes he showed it is possible that one day we can get a glass with lower losses, lower than 20 dB kilometer, and believe me, if you go to the historic, he didn't believe it. He said, it is impossible. Nobody will be able to produce a glass, a pure glass, less than 20 dB per kilometer. And he said, if, and you can read any literature, if one day somebody can reach this 20 dB per kilometer, we will be able to get the optical communication, and the optical communication through the optical fiber will become a reality. And this is something that he was not, he just claimed, and he was not sure. He said, nobody can get that. They forget that there are some chemists who will be able to do that. And these guys, this is corny. This is recently, the Nobel Prize, I will give it if they ask me who will be charged with this. I will share with Hockman, with these guys, because they really did very nice. They changed our history. Because at Cornell, Ronald and Robert and Peter Schultz, together, working together at Cornell, he showed the first things. He made a tube, and he said, okay, if we want to get a higher purity of glasses, forget about the melting process. Forget about the cooking that I showed in the beginning. We need to go another state of material. And what is the pure state? Student?
Yes.
Gas. I will pay communication. Yes, really the vapor state, the gas state is really the state that we have pure state, and we'll be able really to produce a higher quality of optical materials. And this is what they did. And their experiment, if you go to the literature again, they actually start to put inside to deposit particle of silicate, higher temperature, then going to lower temperature, again consolidation, and making all this process and the controlling process, then they reach what we told the first fiber here, 20 dB per kilometers. When I draw here the losses versus the wavelengths, we can see some absorption peak because of some impurity that I am coming back later to explain what is all the time our enemy during this process. Again, a few years later, McChesney, Lucent Technology, said, yes, we can be able to remove this absorption peak, and we will have transmission in all wavelength. This is what we give the vocabulary, all wave fiber. Because in all these wavelengths, we have lower losses, losses that we are talking about 0.2 dB per kilometer. And this is really something that allows us, or allow all the engineering for telecommunication to develop all new systems for communication. Based on that, and based on all that we see, that okay, now the optical fiber is reality. We are being able to produce a higher optical quality. What is the benefit of that? Well, the first thing is lower losses compared to the copper materials, long-haul communication. When I'm talking about communication between Brazil and Canada, between Brazil and France, and all country world, immunity, safety, no need for electrical power, small size. When I talk small size, we are talking about 125 micron. Higher information capacity, what we were told in the world, wide bandwidth, in the way that we can be able to transmit a lot of information beside our video or our internet and other stuff. And one of the important things is low cost. Because any company, if you show them any process, if it's not low capacitor, forget it. This is, I use all the time this word, not the good motor of Ferrari. It is running in Formula 1. The technology coming from the lower price and the higher, the good technology. This is something that really we must think about. And reliability, multiple user, and beyond the telecommunication application, we have other applications that we can show some example today in the way that the optical fiber coming to change our daily life. Okay, let's start about some. Now, what is the basic science? How it look like optical fiber? Today, you are going to the lab with Cesar. We will draw the fiber, but this to understand. We are talking about optical fiber, and sometimes in the literature, some people claim that they are doing optical fiber, but sometimes it is just rod. Please make the difference between rod and preforms. From now we start. We discuss about the preform, we prepare the preform, then we produce the optical fiber. You can use rod and you produce optical fiber, but it's not really an optical fiber. It is optical fiber, but it is another kind of optical fiber because you need another jacketing at the surface, and this is another, it's different for the optical fiber for communication. This is a lot of mistake that I get as a referee in the papers. The first thing, what is the typical structure that we have? We have a core and cladding and then jacket at the surface. Depending on the application that we are looking for, the diameter can be between 8 to 60 micron. The cladding generally is 125 micron, and finally at the end, all fiber, all kind of fiber communications are about 200, including the coating. The double coating is 245 micron. Of course, the measure, or that we know in the literature, we have two types. The single bond fiber, this is what we have been using for communication, that allow us with the whole system of communication, and the multi-mode fiber. What is the difference between monomode and multi-mode? The word, as I said, mono because we have one mode of signal, multi-mode because we have several modes of signal. This is what the difference was. And this is some image that show you the difference also. The diameter of the core is between 3 to 10 micron, and here the diameter is between 25 to 50 micron. And this is the major difference between the monomode and multimode. All the time, when some people ask about optical fiber, what we are talking about monomode or multimode in the way to specify which kind of application that you are being able to using such kind of fibers. Why we said that? Because based on this information that you are preparing at your lab, or you are buying a fiber, based on the information, all the time we'll ask you some question. Which kind of fiber also we are looking for? As we told in the beginning, the monomode or single mode fiber, we will have the difference of refractive index. This is something that we explain why it is important, the refractive index of materials. And we will have here the profile of the refractive index, the step profile, or we have a gradient of refractive difference of refractive index. And finally, this is a single mode fiber with a step index. This is just basic one. Of course, we have different kind of fiber, but the major that you need to learn today. Please, if you understand this, we have gradient index and step index. This is more than enough for the basic science of optical fiber. What's happening here? Okay, if we want to make any optical fiber, there are 4 steps. As you said, we are talking about core, we are talking about cladding, and 4 parameters that we need to control in the way to get some good quality of optical fiber. The first one is the viscosity of materials. This is all the people working in glass. You know what is so important, the viscosity of material. If you are not able to measure the viscosity, go to any specific specialist and please tell them to help you in order to understand what is the viscosity of material. Because I think this is one of the most important. And as I told, I prepared my transparency yesterday. I was looking for for the curve, the viscosity, for different kinds of materials, silica, fluoride, and chalcogenide. And just, I know the reference, go to the reference. I can't remember the reference in 1960, 73, 74. There are curve where you show the different glass, the fragile.
1994, I think. 1994, maybe.
1994. This is his reference. This is a very good reference. Not because he's my friend, but really, this is a very nice reference in the way they show you the different behavior of the viscosity of glasses. And from that, you can get the information if you are able or not to produce your fiber. And this is something, this is the first parameter, viscosity. The second parameter is the expansion coefficient. Remember that we are talking about core and cladding of glass. If we are talking about core and cladding, we must match the coefficient expansion. Otherwise, what will happen? Question to student, another complication. CD will take What will be happening? We have different expansion coefficient.
Losses in transmission due to cracks.
Cracks.
Cracks, yeah.
Good question.
Okay.
Complication, this one. And this is really, this is we have cracks. The third parameters, diffraction index. If we would like to guide this light inside the core, we need to match really, we need to understand what is the difference of diffraction index that we need to use in the way for the application that we are looking for. The fourth parameter, I said viscosity, thermal expansion, and refractive index. The third parameter is thermal stability. This thermal stability of the glass for the core and cladding must be matched in the way that we can get together this glass and we can start to draw the process. And if we control these four parameters, and I come in on one of the important points, why the refractive index is so important. And we can understand this behavior quickly because here what we are looking for, you can use all the physics guys, use all the equation, Maxwell equation in the way to explain how the light, we need the light to be inside the core. And one the important point, this is the basic. Snell law, N1 sinus alpha 1 equal N2 sinus alpha 2. And please use this equation and you will understand that the index of the core must be higher of the index of the cladding if you want to get a transmission inside the core and along the optical fibers. Now, this is not sufficient all the time because what we are looking for, remember that we use the optical fibers for the transmission of light. If we are looking for this at the top of the fiber, we need to understand what is the numerical aperture of this fiber. Because depending on the angle that we will use different behavior of traveling of this light along the fiber, and this is something so important for other property that we will see in the few minutes. This is, when I saw this is I said in the beginning, this is a technological evolution because really there are different parameters that we need to control in the way to get a very good quality of optical fibers. Normally the numerical aperture, it's a very easy equation that we will use. Remember, you can derive this from the first equation and we got this sinus theta maximum of light that we got inside the fiber, and this is square of N1 square minus N2 square. And normally the typical one for the silica fiber is between 0.2 to 0.6, which gave us average angle between 11 to 37, maximum 37. And for that, this will affect what? Will affect the order of type of order that we got for our lights inside the fiber. And this is something that it is important because low order mode will correspond to low angle, and higher order will get us a higher angle, higher rate. This will be each mode. It's given by the velocity of propagation of these lights inside the fiber. And this is so important for different applications depending again of the application of the fiber that we are using. And coming down to the major parameter, the people have been looking all the time, looking during the years for that. Remember the first curve, I told you I like this curve. The change of the history coming from the 16 because we have been able to lower the losses. And lower the losses need to understand what is the mechanism responsible for that. There are different mechanisms that we need to understand in the way to achieve these lower losses for these optical fibers. And the first thing is the intrinsic absorption and depending of the experimental guide. It will depend of what? Of the materials. Which kind of material we are using. And this is in different region, in UV, visible or IR region. In these three regions, remember, we are talking about the losses versus wavelength in UV, invisible, and the infrared. These three regions for us, it's so important if we want to get these low losses. And let's understand everyone. The first one, the UV region. In the UV region, who is responsible for that? On the occasion game. Not for me. Okay. Students.
It's written down.
Don't tell me. Who's responsible in the UV region? Who's responsible for this?
So we blame him.
Yeah. Exactly. In the UV region, who is responsible for the absorption? What we have in the UV region? Raman, help.
I'm just saying, what's responsible for the loss in the UV region?
What would be the reasons for the loss in the UV, in the short wavelength? Is there something happening out there?
The absorption of light by electrons.
Listen, electrons, remember, basic balance and conductive balance. This is, remember these two levels, and this is so important for us. It's not so, in our case, it's not so important because depending on the material we are using, and I give an example here for silica, we are using 140 nanometer, and for germanium it's 185. For phosphate, it's 220. For fluoride, it's 240, etc. Depending on the starting, this is what I said in the beginning. The component of material that you are using, it's so important, and it's the parameter that you will use depending on the application that you are using for. For the chalcogenide, it's far away. It's something like 600 nanometers. Or, and again, depending on material, some of them is 900 nanometers. And this is sometimes, we need to define in the beginning, before that we start to make our cooking. Before I cook my material, I need to understand what is the behavior of the material, what is the intrinsic absorption in the UV region. This is the first one. And this is, of course, this is based on the equation we can derive from this curve, we determine the lambda zero. The second point, the infrared region. Who is the limitation for the infrared region? Chemists. Basic. Excellent. This is vibration. Multiform. And all this, again, is chemistry, depending of vibrational mode of the material that we are using. This is something that we need to understand in the way that will give us our expectation, what we are looking for at the end, if it is reality or not. If it is not reality, something is happened during my process of preparation. In the way that I can predict what I can prepare or not. Otherwise, I said, it's cool. And this is in silica glass, it is this equation, and this is a constant exponential minus another constant slash lambda. And this is, once a lambda, this is something, it's very important, that when you see it in the curve, will be something like that. Remember in the UV, we are coming with this curve, and the infrared, we are coming with this curve. If we put two together, we have a V. This is what we call the V curve. And this is very important to us because depending on this, the minimum of this V curve and the specific wavelength, it will determine, theoretically, I can make the theoretical model before I start my experiment. And this is so important because I can predict again what is the minimum losses of my materials. And they said, if we found some really deeper losses, we just share the Nobel Prize. Because it will be new in the literature. And this is challenge. It's another new challenge for development of technology that we are looking for. Didn't finish yet. This is the first part determined as the V curve. But between this V curve in this wavelength, nothing is perfect in the nature, and what we have here, absorption, is not depending for us, depending again of the impurity of material, something that sometimes starting material, or sometimes during our process we'll get some absorption, some impurity during the melting process. And the major of them is metal transition. Again, all our enemy, chromium, manganese, ferro, nickel, etc., all these transition metal, independently of yours, when you buy your starting material, please check all the time. What is the absorption at specific wavelength of this transition metal? 1 ppm of that, forget it. If you are looking for 0.0 dB per kilo. If you are looking for higher, for really low losses, 1 dB, it's a lot. We are talking about party per billion if we would like to check, to reach lower losses. And if we would like party per billion, we need to go to vapor phase. In the solid state, forget it, never will you get that. Because all the time, when you buy your material, you have some impurities inside your starting material. Independently of the company that you are buying from it. Another thing is that, please, listen, when you buy any chemical product, before you start your experiment, make a simple things, make a spectra, in the way to check if what these guys are saying is the sign as in the bottle. I can tell you we have 1 party per million, but we have more than that. And the experiments show us during my lab all the time we have wrong data have been provided by the company. The other major problem of that hydroxy group. This is the worst thing. And hey, this is something that's depending for us, or this is something this is bounding during to the molecular during the process of formation, and this is something that we need how to avoid that. And remember the curve that I showed in the beginning when you showed the losses versus wavelength. Remember what Mark Chesney he said. Yes, we will be able to do all in all wavelength. We can remove this peak. This peak, I didn't say in the beginning it's OH group. OH group in the silica, the fundamental of that is 202.9 micron or 1.4 micron, 0.995 and 1.224. Did you see several absorption of OH group that affects the optical quality of the fiber? We solve all these problems. Okay, now we have materials. We have another problem again. The scattering, because this is something that will depend on the process, and again depending on the materials, because the fluctuation or the microscopic fluctuation inside the material will affect the subwavelength, and in this case we will have some scattering, what we call raining scattering, that we can measure also. And in silica glasses, it depends in general when we dope with germanium in the way, remember, to change the refractive index of the materials. we'll have a fluctuation of the intensity, and in this case, we will have some scattering. And the main of that, if you want to check that clearly, please go to the visible and near infrared beyond 1.66 micron, and you will get you will see some scattering, which is due to arriving scattering. Again, you control all your parameters. You have good product, you have high purity materials, and again, the process now, it's a parameter of your production, because this time, the imperfection is coming, the giving light, and this imperfection of the giving light, because sometimes we have some irregularity and the interface between core and cladding. Remember, core and cladding, we must match the expansion coefficient, we must match the viscosity of that. And sometimes, depending on the viscosity of that, we will have some problem of the interface of core and cladding, and this will affect the property of the optical fiber. And this defect sometimes, generally, it's lower than 0.5 dB per kilometer for silica fiber. When we solve again this problem, we have another one. Another one, this time, is coming from the bending losses. Bending losses, as I said in the beginning, the fiber, this is a glass, core and cladding with a jacket, with the polymers, and when you bend your fiber, this angle, depending on the angle that or radius that of your fiber, sometimes we are going thinner, you will have some distortion, and distortion due to the bending, it's coming from what? From distortion of the profile of the refractive index, which can explain by this equation. And we can measure that, and in this paper of Marcus, he showed these losses of the bending will depend mainly to radius, and also two parameters here, lambda c to lambda, and again the fluctuation of the bending. And this is sometimes that if we measure this parameter, we can measure the losses of the bending. For 2 centimeters, it's 1 dB per kilometer, but for 1 centimeter, it's something 10 to 4 dB per kilometer. It's too high. And this is something independent for us. We have, because of the bending, we have these losses. And remember, why today still have the connection just coming not to your inside your home, but outside the home, because now you're looking how to get some system, what we say home to home, and inside your home to get fibers, because of the bending. In Japan or other countries, they are using what we call plastic fiber, but in other countries, they still believe in silica fiber, and now it's coming to report that I said in the beginning, in 2007, Corning showed that they have been able to get some bending losses that are predicted in the theoretical or experimental data reported there today. And this is the behavior of optical losses that I saw in the beginning, that I explained in the curve, in the Y attenuation and versus wavelength, and we have all these parameters. The total one, which is coming from UV plus infrared and Rayleigh scattering, all together they give us this total curve, and this give us the minimum of the losses at specific wavelength. And typically for silica fiber, it's something around 1.55 what we told in the telecommunication word is C-band, central band. Why the central band all the time? Why 1.55? Because at 1.55 we have lower losses, we reach 0.2 dB per kilometer. This is the answer to the question. Okay, besides that, we have also what we need to measure the dispersion. The dispersion curve, this is something that's so important because this will affect the signal of our light, and this is so important again. This is 2 parameters because it will depend from the dispersion of materials coming from the refractive index of the materials, and again, the dispersion due to the waveguide. And if you attend one day the courses of real body, he did all the theory of that physical thing, explain really each component of that, and the total of that will give us the total dispersion or the zero dispersion at specific wavelength. Why we are looking for the zero dispersion? Because if you have any positive or negative value will affect the signal of your transmission light, and this is something that's coming with some noises in the signal that we have. Generally, when you buy any fiber, the standard that the information that we gave you, that we taught, this is, I give the example of Corning. Please, Corning doesn't pay nothing for me. Just I pick up the example from the internet, just to understand that. This single mode fiber 28, this is the characteristic that you need to check all the time. What is the attenuation and specific wavelength? What is the cutoff? What is the modified diameter at the specific wavelength? What is the numerical aperture? What is the zero dispersion at specific wavelength? What is this slope of the zero dispersion? And what is the core cladding constantly? All these parameters we need to give it. Also, at the same time when we are preparing our fiber, all this information we prepare in order to give to our guests or our collaborators. Because this is so important for them. I just want to show this transparency because we have other kind. This is so important. Beside this side that we have been talking about, the core, solid core glass, sometimes we have a hollow core fibers. And with this hollow core, it's so important also to guide the light for a specific application. Again, we can make a metallic cladding, we can get a multi-layer that we have different process of getting light, or finally we can get a 2D photonic crystal cladding. And in this case, for us, some specific applications, some specific traveling of light, it's very important for you to get some fiber. Just to show you, this is, in contrast to solid fiber, they are also, the hollow core fiber are also so important. And maybe today, Cesar said in the beginning, what you will prepare today, what he will draw today, not a preform, but he will draw a capillary, hollow, he will pick up a hollow system and he will draw the fiber. If that we what you will have the experiment today, you will have something like hollow core fibers. Just a few words about mechanical property because I saw that I need to get fast. It's so important, the mechanical property, as I said in the beginning, because of the bending and also for the safety, and also if I need to deliver any optical fiber, I need to give in the contract 20 years of guarantee my fiber will be safely and will transmit will have transmission of light. Imagine if the band will have after just 1 year a problem in it, all their gas will be unhappy with that. And for that, the first thing, we draw the curve of stress against that. This is the basic of the mechanical property of any materials, and the behavior of that, it can be elastic, ductile, or plastic. In the case of optical fiber, it's a elastic behavior, and this is dependent because of the bend strength atom of silica. This is something around 20 gigapascal, or something you say in the literature in megapc. And in general, for the glass fiber, the strength is around 4 to 6 gigapascal. And the main problem of that is we haven't time to discuss deeply on that. The main problem is surface flow distribution. And there are several theories on that. There are one theory based on statistic measurement, and there are some people just working on that all the time in the way to specify how to get a higher quality of mechanical property of the fiber. And one of the things that they did when they measured that, because this strength of the fiber will depend on the length. If we are talking about 20 kilometers, 1 kilometer is different behavior. Strength rate, the temperature, what is the relative humidity that we are talking about, and finally, what is the chemical and mechanical induced flow in your surface of the fiber. When I am talking about the surface, I am talking about the surface of the cladding, or sometimes, including the polymers, the polymer primary and secondary polymer, we have some defects at the polymer, and this will affect the mechanical property of the fiber. Of course, one of the tests that we did, any company or any lab in the world, specific lab, that you need to deliver a higher quality of the fiber, you need to make the proof testing. The proof testing is based on in the information of what is the loss that we need to give in the way to make this measurement, and this is something that's usual of our company. But I said I said in the beginning, this is something so important. I want to spend just a few minutes on that. Cornell recently showed, okay, how we can improve the mechanical properties. How we will be able one day to get one fiber that with a higher mechanical property, and Cornell again in 2007, you can see here, this is one, the show kind of fiber, this is several fiber, optical fiber, and this is the tight bonding. This is lower than 1 centimeter. The challenge of that is several one. The first one, if you look at the literature, carefully in the literature, there are different techniques that allow us to get a higher mechanical properties, and one of them, we can reduce the mode field diameters in the way to enhance the mechanical property of the fiber, but this is not so enough. And again, in the experimental point of view, it's very hard to get lower than sometimes 5 microns. Using the MCVD technique that we are coming with, I will explain, it's almost impossible. And this is what, using this technique, is a big challenge. The second thing is, by depressing the cladding. Depressing the cladding, in this case, I will change the expansion coefficient, and in this case, I will have stress and enhance the mechanical property of this fiber. Again, another challenge, and it's not so higher comparing to the silica standard one. The third one, we can add it a low index profiling the fiber, another design in the way to enhance it works, but the price is so expensive. And normally we have a higher dopant of germanium, and when we have a higher concentration of germanium, we have another problem, photosensitivity and other stuff. And this is what the people avoid to use such fiber. Recently, again, Corey, we show, yes, we will be able to do what we told, a fiber with the structure, what we told microstructure, with symmetric holes, and allow them to get a higher bending. Or insensitive to bending, insensitive to bending. Do it in the way that you want. And this is something open the door for mainly for the telecommunication application. We can get, using now this fiber, I can get this in my house, we can get this for other applications. Again, what's the problem with that? Price. And you have been enabled to produce higher than 20 kilometers in one step. And this is avoidable to go to the market. The claim date is something like around 2006 or 5, and they have not been able to sell it in the market. And recently, they made another geometry. That this time, they get the price, and they get lower bending than the comparing to this symmetric bending. What we told this time, we have a core and cladding, we have a nanostructure here. This is like similar horrible. He didn't say nothing about that. He didn't explain, really. I tried to understand how he did that. I haven't the answer. Hopefully, one day we will try to do that very it's okay. But this is something, it's really amazing. Because as you can see here in the picture, really, and they show, we haven't time here, they show the profile of the lights. It's really the same quality as any optical transmission system. We maintain the same quality of the signal, of telecom signal. And we maintain the same losses, and we maintain all the optical properties. And this is something new. In 2010, they came to market, and now they are selling one bed for 50 kilometers. Again, I don't know what is the price. I'm sure that the price is something so expensive. Quickly, what is the fabrication method of that? Yeah. Nice. What about that? He's my friend. Optical fiber cannot. We are the different things. It's from the glass, polycrystalline, monocrystalline, or polymers, depending of the material that we would like to pull fibers. We have different techniques, and one the major one is CVD technique. From the preform, fiber drawing, rolling to we made a fiber drawing, cast preform, double crucible. This is a direct draw, double crucible, because we are liquid state together, core and cladding will draw together, and soldier preforms and stuffing draw. This is a photolithography fibers. What we would like to focus here just in this part, as you can see, different techniques have been developed during the years based on modified chemical vapor deposition, plasma vapor deposition, over vapor deposition, or vapor axial deposition. Why of that? Depending the company, Japanese company, English company, American company, etc. Depending of the patent that they have been, they just change one technique, so one word, and they put one word before and they said, this is my technique or my technology. This is how it works. And what is important here, I want to know that in the vapor axial deposition, because this allows this company to make a large preform. When I say the large preform, it's something like 1.5 meters. And this is allowed them to make kilometer and kilometer of fiber, and allowed them to make.
Can I just take a comment on that?
Yeah, please.
It's very interesting. I've seen a preform which was something like 12 feet tall.
12 feet tall?
Some Sumitomo. Huge. Actually,
3.5.
3.5 meters.
massive. It stretches across floors.
Rather, he said
It's about
3.5.
this diameter.
Yeah. This is true what he said, because he saw, what I saw 1.5, he saw 3.5, but the diameter, it's, how much it was diameter? It was big. It was big. It was something big.
So you need a few physics to put this in the
But because of the price, again, we're discussing about the price, how we can lower the price. I remember the time that we Corning and everybody have been doing just by MCP. Here in Brazil, we did a telegraph company. They did the technology, everything, but the price, they didn't reach the price because the process was so expensive compared to the large one. And this is the competition of this market. This is, I told your chemist or physicist, please draw new technology in the way to lower the price more and more. Just for the polymer, here in Araraquara, we haven't done so well, but here in Araraquara we have the extrusion process that allow us to make the polymeric fibers beside the drawing, standard drawing process one. Quickly, we haven't time just to explain the difference over vapor deposition or axial vapor deposition. We have what we told a target here or rod, and we'll deposit around this rod. All these particles, vapor phase, will deposit around this rod, and we'll have a large preforms. What we are doing at COP, this is, we haven't here in Araraquara, but at COP in Quebec we have that. You are welcome all the time if you want to make any kind of preform. Of course, you need to pay for that. The modified chemical vapor deposition, this is Nicola doing his system. As we start with a tube, and here, quickly, this is the main process that we are doing. I want to spend just a few minutes on that. This is very important, and to show you really the technological behavior of that. We start from different chemical elements, depending, again, we want to match the specific property. Remember the four properties that we speak about a little bit. Now, we start with this chemical deposition, then we want to change the refractive index, we put the germanium, or again, we want to lower again a little bit the refractive index, we go with the phosphorus, and this is coming, we have a controller-free system, and coming inside our rod tube. Normally we buy this rod tube, this is from the Heraus company, a higher quality, it's very expensive of course, it's a higher quality, with a high purity of silica pure glass at SaO2, and we make deposition inside this material, and you can see here these particles we have in the vapor phase, remember, and here we control what we call the oxidation process. Remember, we have decomposition here, higher temperature, silica chloride, and with oxygen, we have formation of higher particles, what we call nanoparticle of silica. If people speak about, lots of nanoparticles of silica we have here at glass at the end, and after that, we just make consolidation process, and you get the cladding and the core of your reform. Of course, all the detail of this process will have this transparency, all the detail of the salt formation, all the substrate, the whole substrate inside, you will have through this oxidation process. We have formation of silica, germanium, and phosphorus in the way to control the refractive index. Just to give an image of backscattering electron for the inside, this is a profile of the different layer of the core of a green preform. You can see, this is each layer you deposit. We can see clearly what is the homogeneity of this layer in the way to control the behavior of this process. And at the end, we measure the profile of the refractive index to show clearly if really we reach what we are looking for, the difference of refractive index, and also difference of the core. This is a monomode fiber with 9 micro of the core and 125 of the cladding. Of course, there are other process. This process of silica that I saw in the beginning using vapor deposition, but for other kind of glasses, fluoride or capuchin glass, we are unable yet. I told yet because we have years, there are years in the way to develop this technology. But one of the technologies that we use, what we call rotational casting method, we have a mold here, we pour our glass, we have the cladding rotational system, we have a tube, and then change the angle, we pour the core, and then we get our core and cladding preforms. Of course, one of the important things again, the coating system. The coating system will depend 2 points, it's environmental protection, and sometimes it's very important for sensing. We have different applications just using the coating, and why the protection against abrasion, against hydrogen diffusion, against chemical attacks, against temperature resistance and mechanical bending. What I speak a little. And sensing, because sometimes we use a specific coating at the surface because we have some fluorescence, we will make some fluorescence measurement for some sensing experiments. We have some bioactive system, and Benny spoke a little bit yesterday about that. Magnetic process, acoustic piezoelectric processes that we are looking for. As I told sometimes, not only the core and cladding is so important, but the coating also at the surface is so important, and because of the property that we are looking for. Just I give this transparency to show you the different coating that we have been able to have, and also the range of stability of temperature of such coating. Now, the first one is acrylate, which is stable between -50 to 100 degrees C. Epoxy till 150, polyethylene till 180, silicone, which is a lot of that we use between -20 till 190, and polyimide, this is a lot of application of that, which is stable till 280, and finally metal layers or metal coating. This is so important because it's covered a large range of temperature till 500 degrees C. Of course, one time you finish all that, you go to drawing tower. This is our drawing tower at COPL, and Steve is maybe waiting the process of drawing. And one of the things that we are doing today, and one of the important point, he will be waiting of what we call softening temperature. Softening temperature is the same thing as the glass transition temperature. This is one question. Foundation. Again, softening temperature is the same thing as the glass transition temperature.
Yes.
Excellent. Pay for me foundation because now. Okay. Give me more 5 minutes. Thank you. Student, not for you. Softening temperature is the same thing as the glass transition, because all the time I heard about I this is why I asked. Julian, now. Yeah, no coffee break today for this year. If you didn't answer, no coffee break. Choose your. What is the problem? The word softening temperature. What I would like to do? I would like to draw the fire. Okay? Soft. Okay? Glass transition temperature. You remember? You made the experiment now. What is it? Everybody made the AC curve? Remember the AC curve? Quickly. Flow, energy, temperature. We have something like that. This is the line. Endothermic process. Remember that exothermic process? And what we have? Something like that. Where is the transition temperature? Where here? Just flexion. Here. This is the transition temperature, and here what we have? Quickly. What we have here? Maximum, and here, melting temperature. Where is the softening temperature? Here. It's here, here, or here.
A few degrees above DG. To right of DG.
Here.
TG and TX.
And where here?
In the middle.
Between TG and TX.
Yeah, between and where? And this is it.
At the second curve.
It's here.
No, second.
Second?
Yes.
Here.
Yeah.
Close.
Yeah.
You almost everything today. What happened to you? Give him more coffee today. Come on, what is the problem? Remember, what's the parameter that I said in the beginning? What's the first parameter? Viscosity. Give him more coffee. No, more complicated. The viscosity is so important. This is so important. If we want to make any optical fiber. The viscosity, and I told all the time, when you make your curve, try to make again, drop your viscosity curve in the way to see where your softening temperature. Normally, the softening temperature for drawing the fiber, the viscosity is between 10 to 4 to 10 to 6 plus. And here at the transition temperature, the viscosity is too high. What is the value of the viscosity at TG? Murillo, you know that. I remember I gave it in my class. You have been my student. Give him promotion. His professor is here. Kill me, please. This is the word that I always answer or one K. This is one thing. I can't do that in Canada. I know where I am. What's in the viscosity at TG?
Infinite. Infinite.
No.
It's 10 to 12 Pascal per second. Per 10 to 12 Pascal.
Excellent. 10 to 12. This is around 10 to 12 or 10 to 14 plus. We are talking that it's solid. We can draw it at TG. And this is so important. I saw all the time a lot of mistake of that between the people making the mistake between softening temperature and TG and this speak again papers. I saw that. This is so wrong. When we are talking, please, this is so important. The softening temperature is something like 10 to 4 to the 6. When we can draw the fiber, this is why it's so important that we need to make the viscosity measurement. You will speak about that? About simplifier? Yeah. Okay. Okay. One of the challenge of development for the optical fiber communication is the development of fiber amplifier. Remember, if every 40 or 50 kilometers we need to amplify the signal because the signal is coming too low. And for that, one of the things have been developed in the 64 Snyder he showed. It was possible in applied optics, in his papers, it was possible to make a fiber doped with neodymium, and this time he shows a fiber amplifier at 1.06 micron. And the behavior of that, if we would like now, the fiber at 1.55, we need to choose adequate rare edge element that will emit at this wavelength. And remember that, where is mine? It's here. Okay. Remember that what we are doing is here. It's lower losses of the optical fiber. This is the absorption of OH group. And here at 1.55, we need to show what is the adequate element in the way that you make this fiber amplifier. And the adequate element is erbium. And this is something that Snyder saw. It was so perfect because erbium it emits at 1.5, and beside that, they have the lifetime of the emission is something like 10 milliseconds, which is so important for the application. Why? Remember the principle of that. It's we have ions at the lower level, and we pump to excitate at a higher level, and the not spontaneous emission. If we have spontaneous emission, it will be a defect, but under excitation, all these ions with the signal it's coming here with will be amplified, and this is the process for the fiber process that have been developed by Snyder. This is something that changed again the world of communication, because this time we will be coupling the optical fiber, the monomer fiber, silica fiber, with the fiber amplifier. Of course, at Araraquara in 2005, in the PhD thesis of Eduardo, we have been working with Ericsson for developing this time another kind of optical amplifier, and just coming back. And our challenge was with Ericsson S-band is around 1.40 micron. At 1.40 micron, we have been looking what is the red X element that allow us to get emission at 1.4, and in this case, the adequate one, you can adopt silica, but the emission efficiency is too low, and we have been looking to develop a new kind of glass. This is the work that have been developed by Eduardo in his thesis. He developed a fiber amplifier based in modified germanium glasses, which we have a large emission that cover not only the S-band, but also it cover the C-band. It was so important, and the Ericsson deposited the patent in 2005 in the way to use shotguns of fiber amplifier. Of course, in the chronology development, I didn't put some change during the years. In '74, Marcel Pounet in France at the university, he showed a new kind of glass. Discovered a new kind of glass. This time based in zirconia, barium, lanthanum, aluminium, sodium fluoride. All these elements is fluoride. We're not discussing about the silica glass this time. What this fluoride glass is different behavior than silica glass. It's different viscosity, and again, it's difficult chemical bonding behaviors. And the dream at that time was, because they made the theoretical Vickers, and they show with this fluoride glass we'll be able to reach almost 10 to minus 3 dB per kilometer. That's around 2.4 micron. And everybody was excited and okay, we'll change all the communication network system. And at that time, all the installation in AC State, almost 90% of the installation was made in silica. How will change all the silica using the fluoride glasses? Just after 2 years or 4 years, the dream of everybody was changed, because we have been enabled to get this theoretical value. The theoretical value, the experimental value today, it's around the base in the base way. It's 10 dB per kilometer at 2.4. And this is something because of the process of preparation and also for the technology. what we did at that time also, this is during my PhD thesis, we discovered a new kind of glasses based in indium fluoride, what we call fluorine glasses, because it have higher transparency than silicon, than fluoride glasses. Fluoride glass comparing to silica, it's transparent till 5 micron. Remember, silica is till 2 micron, which open a large application. Maybe Rhea will cover all this with this part. He will cover all the application of the fluoride glasses. Oh, of course, I recommend to go to these papers of Stewart Jackson in Nature Photonic when he gave an overview of the characteristics of the laser fibers that today can be possible in the different wavelength from 600 nanometer till 4 micron, and all the possibility using oxide glasses with the power and density of this laser, and maybe here we'll cover that, and also the fluoride glasses. This is a nice overview of the fiber. Of course, not sure if we'll have time with that, but one of the important technology that have been developed in 91 is this microstructure part, because really it will change again the thing of how we can be able to develop new technology based on this fiber, and it was possible because this time we will have a very large refractive index between the core and cladding. Typically in the silica fiber it's something like 10 to minus 2 between the core and cladding. Here we are talking about something 0.45 or 3 to 10 to minus 2, depending on the application that we are looking for. This is one thing. The second thing, this is important point, that all this void we have, this is a microstructure fiber, all this void, we can fill it with a specific material, with a specific polymer, in the way that you use it for sensing, for electrical application, or for optoelectrical application. This is something new, and this is something that can be used for sensing temperature, for sensing of pressure, etc. Of course, what I want just to clarify here, please, when you look for the photonic crystal fiber, you need to classify. We have different kind of microstructure photonic crystal fiber, and in this case, I divide here what we call the higher index core, index gating, holy fiber or holy assisted fibers, or photonic band gap. The photonic band gap, the people make the mistake all the time. Photonic band gap and microstructure, and they make the connection between two. This is a two different behavior and two different application. And you can see here, because the behavior of the geometry of the fiber is too different. And this is so important for us in the way if you want to understand the physics and chemistry of that. Because we have a higher numerical aperture here, but we can't get it here. We have a large known area. We have a highly nonlinear process if we get a thinner core, less than, let's say, 3 micron or 4 micron. Today we are able in the lab to make a 2 micron, which enhance the high nonlinearity process of the fiber. And of course, in the photonic band gap, we have a low index core, and we have here, the light is getting inside the air. Remember the picture that I showed in the beginning when I showed this hollow fiber with the core, and this is photonic band gap. Of course, the process of that and the different, it's explained here. I haven't time to go to that. And I explained the difference between the photonic band gap and the other process. How to mine this fiber? And this is, again, the challenge for the experimenter, for Cesar, or for Steve. These guys, they spend a week just to prepare this report. They put together all this row, and then they go, they stop, and they go to the drawing machine, and they put together, and using specific technique, of course, gas and controlling atmosphere, controlling temperature, and he draw the fiber, and we have what we call these hollow microstructure fibers, depending the specific application that we have. The different application, they open a large area of application. One of them in the telecommunication, some of them are using for dispersion, compensation, or broadband fibers. For the laser, we use generally for double clad fiber for large cavity, or large area fiber for higher power transmission, or also for making white light sources. I think in the 90, I remember the first white light using this fiber have been, 96 white light sources have been produced using such kind of fiber. Of course, there are several applications, let's say sensing, metrology, medical application, and one of the medical applications today is optical, or OCT, optical coherence tomography. This is some specific application like gas sensors, or also, as I said, the ultra band white light sources in this paper in 99 in electro-optic. In this paper, he showed this ultra band light of fiber. Okay. Sorry guys, I will go fast here. Forget this, all these things. Without this transparency. This is because I prepared this.
They will have.
Huh?
They will have.
You will have the presentation. Okay. What is it? I would like to spend the 10 minutes for this perplexity. What is our dream? What the people are looking today for? And please read this paper. It's very interesting. Lightweight technology in the show. You have this paper again?
Yes. Anita was my student.
Yeah. He was his student. Wow. In fact, the show, what is the evolution of record capacity of optical fiber, which we are looking for the next. In Canada, we are talking about 100, which is the capacity today. It's 100. Yeah, 100 giga. Yeah, it's 100 giga in Canada. But I was in a meeting in Ottawa 2 weeks ago, no, 1 month ago, and they said it was 400. Sorry, they had the company there. They show 400 and 1 terabit. They have in the lab running for it. The capacity of all the people are looking for it. And 400 is already going to the market. I think in Brazil we are talking about 40 giga. And in Europe it's something like 100. In France it's something like 100 gigabit. And during the year, this evolution, I don't know where it is going. Because it's depending of our demand, of our, I think, what I said all the time, not for us, for our children, maybe they were using this capacity. And one of the things that we have been developing at Laval University, it's to attend this demand of higher capacity, we need amplifier. And one of the things of the work that we are doing with Sophie La Rochelle, it's calling engineering telecom, we can be able to make a multi-core fiber amplifier, and in this case what we did, this is a optical fiber with a core coupled with erbium, and we have this 7 core here. The challenge of that, how we cover that. Of course, there are several programs of that, but one of the things that we are happy to say, we did it in the fiber. We have been able, after 8 months, we reached to do the fiber with the request of the engineering telecom. The second point, this is a joint work with Denis Boudreau, my friend, of course. He produced a high quality of, he controlled the quality of nanoparticles, depending on the geometry, on also the diameter. And one of the things it is important, we fill it inside the microstructure fiber, chalcogenide fiber, we fill it this Maxime, of course, he did this work, Maxime is here. And he filled it inside using a specific high technology, I can't say it. He filled it in whole the fiber, homogeneous process. I think half meter, 10 centimeters. I can't remember. He's sleeping. Don't go. You can sleep. You can sleep. No problem. It's 1 minute. it's homogeneous in a whole. This is what was very important really. In a whole, the fiber we have a homogeneous. And this is, we can look with silver or gold, here another platinum. This is, it will open for us the door for other practical application. Another challenge that with Ottawa, they asked us if we will be able to produce electro-optical fibers, and in this case, the technology as follow is their design was with 2 core and this specific diameter of geometry, and also we actually were working hard on that. Just before I came here, discussing with Nicola, he said we reached the preform and we coming to the fiber after 3 months of processing these systems. Again, with the engineering people, which we have been doing it, what we call a highly doped ytterbium fibers. This is a specific geometry. Again, it spans more than 6 months in the way to develop. This is a cladding, and beyond the core, we have a higher concentration of germanium. And inside the core again, we have higher concentration of germanium and also doped with a specific amount of ytterbium. And we get this specification of the fiber, and you can see the modified diameter of the core is something like 4 micron. And we get the absorption of the ytterbium. It's higher than 500 dB per meter at 915 nanometers. Of course, one of the challenges have been developing by Real Valley and another research group, neurosurgical department, if the connect. This is I found a very nice work have been published in Nature method by a PhD student of Professor Real. When they have been able this science for life science and for neurosurgical application, they have been able to produce a specific fiber with a tip 10 micron that they can sense the neuron, which is again the size of the neuron is 10 micron, and they have here a hollow core, specific core, filled with an electrical solution in the way that they can get an electrical measurement of this fiber. This is a gradient index fiber with a hole here. This is this hole, this core that is filled with this solution for electrical measurement. The electrical resistance is around 6 to 26 mega ohm. One drawback of that is the instability of the derivative medium. And we have been working together since they published this work last year. We have been working together in the way how to enhance the quality of the fiber in the way to transfer this technology to a company. And recently, we have been able to show another, beside this technology, to show another possibility this is the work of Maxime again. He showed another design using the several requirements. First one, we have the cladding, another conductive materials, and the core of the fiber. Now, the requirement of that, we need a conductivity, it's around 10 to minus 0 cents per centimeter, higher than 70% transmission in divisible wavelength. Viscosity of the component similar. Thermal expansion for the 3 glasses similar, and again mechanical and chemical stability. It's a tough work, but this is his PhD. Has long way in the way that he can develop such fiber. We are in a good shape because we have already deposited a patent on that, because really we show that all these 3 requirements of the glass we developed already. We know which kind of glass that we will be able to use, and also which kind of conductive, which will answer the first question and also the second question. Of course, one of the things that have been developed at INO, besides the Center of Optical Photometry Laser and the Institut National of Optics at Quebec also, this is a big center, more than, it's close to 400 researchers. They developed a sensor for nitrogen, phosphorus, and potassium, and this is based on an optical fiber system. This is a very challenge for agriculture. because they use what we told this system this time a membrane selected for ammonium. The first experiment that they use using evanescent wavelength for NO3 minus, and now they are working for phosphorus, and they work for pH, they work for hydrogen, they work for several elements for calcium. They have a patent on that. They did a very nice work on this development. Of course, I hope that I answered to all this, cover a little bit about the optical fiber, fundamental, on which kind of application. Please forget me if I forget something. At the end, I would like the thanks on a research group at Quebec. You are welcome at the winter time, of course. And of course, the photonic material group here at University that we have still have, like, see they are, where is the other student in the city? Yeah, maybe they are in the bar or something. Thank you very much.
Thank you, Younes. Questions?
I will not answer your question because you didn't answer it.
I want to apologize for actually failing that question. Maybe I was in a hurry to answer.
No, please go on.
I was in a hurry to answer. I shouldn't have failed it. I want to find out. You talked about the softening temperature.
Yeah.
Yeah, not being the same as the TG. Now I understand. But how do we determine it? Because there is a range there from TG, the point of TG and the TS. Yeah. Is it softening temperature within that range? And then how do you pinpoint it?
Excellent point.
And the softening temperature.
Sorry, I was so fast. Perfect. Let's just take, this is the G. And here we have the inset of crystallization. Okay? Here, never you will find softening temperature. Using the C curve, never you will see it. Okay? This is what I told you. We need all the time to make the viscosity measurement of your glass. Without that, you can't know it. Okay? Never the DC curve give us the characteristic temperature of the glass. What's the characteristic temperature? TG. Crystallization and melting. Or any other event, oxidation or reduction process. The softening temperature will never get.
So in the process of drawing the fiber or waiting for the fiber to flow, you
need to go.
Yeah, you need to measure
the viscosity.
The viscosity intermittently.
Oh, of course.
Okay.
You need to measure that.
Yeah, it's okay. It's like the melt flow index in plastics.
Yeah.
Right.
This is something so important as this for all the glass people that they have. What I said all the time, they need a viscosity in the lab. Otherwise, we are making kitchen. We are cooking. Go ahead.
There's a new development in calorimetry. Just wondering whether that answer you just gave may be about to change, because there are people, there are developments in calorimetry, nanocalorimetry now, where there's a good group in Barcelona, for instance, Schick in Germany, where they're scanning at 10 to the 4th K per second, and I think that the TG you get under those circumstances will look like this, but it might represent it will represent a much shorter relaxation time, and could be probably adjusted to give you the softening temperature directly, you know, the relation between the enthalpy relaxation time, which this is measuring, and the viscosity.
Yeah, in fact, we can use TMA, thermal mechanical analysis, in the way to get the softening temperature. But this is a thermal analysis, but we're using the thermal mechanical analysis. I can measure the expansion coefficient, and with the expansion coefficient, at the maximum peak, here, I can determine the temperature of softening temperature. Yeah, like DR technique. But again, this is, as you know, this is using this is thermomechanical analysis, but I believe more in the viscosity. Because all the time when we measure, we have difference. Sometimes it's more than 50 degrees C.
Can I take advantage of having the microphone to ask another question? It's about the fundamental absorptivity, that the part of the diagram you showed which relates to Rayleigh scattering, which is determined by the density fluctuations frozen in the glass. Now, I know the compressibility which is related to those density fluctuations is decreasing with fictive temperature. You freeze in a very high fictive temperature when you make the fiber. What are the prospects of getting fibers of lower fictive temperature which would have lower Rayleigh scattering?
I think we use that, but in fact there was some problem of mechanical problem of fibers. Actually, it's the case. You decrease by reducing the fictive temperature.
Reduce the Rayleigh scattering.
We show that, but there is some mechanical problem.
That's right. Yeah, that's true. I mean, that was done regularly in the early days to just reduce Rayleigh scatter because of fictive temperature. But yes, you're right, there were issues. And I think sometimes you do use it when you want a specialty fiber, and you know, mechanical strength is not an issue. So.
Thank you.
I would like to know what's the loss when you connect two fibers, and if the process of connection has been improved with the years.
You mean we are connecting the fiber, what is the losses? Typically 0.1? Splicing, yeah, when we are splicing the fiber. It's 0.1. Less than this. Yes. I don't know. It's usually the best.
There are several methods of connecting fibers together. One is a connector, where the losses could typically be 0.1, 0.2, 0.3 dBs, depending on the type of fiber it is, single mode. Multi-mode, it could be higher or lower, depending on the quality. The second thing is that if you were to melt splice them together, which is fusion splice them with an arc, and typically this is what is done with single mode fiber. If the fibers are perfectly identical, you can get sub 0.1 dB losses regularly. It could be even as low as 0.01 dBs of loss, but typically you would get losses of about 0.1 dB. If they are dissimilar fibers, that is, if you take a standard, the SMF28 fiber, and you want to connect it to a dispersion shifted fiber which has a lot more germanium, because of the difference in melt temperature, you can get a much higher loss simply because of two things. One, the modes in each side of the fiber, that is in the standard fiber and the dispersion shifted fiber, the sizes are different, therefore there's a mismatch. But if you work very carefully, what you can do is you can enlarge the mode size by heating one fiber more than the other. And that way you can have a very slow transition in the mode size from one fiber to the other and get very low losses, typically about 0.1 dBs. You can get them, but you have to work hard. Okay. I hope that answers your question.
Just so much. The fiberglass used for composites, is it the same with this? I mean, the fiberglass fibers for composites, make composites.
Oh, okay.
Yeah.
Yes.
Is it the same with this? I know that one does not have core.
No. Thank you for this question. I didn't mention here. The fiberglass that you can use for construction or other application, it's borosilicate glasses, it's a cheap glass. And you have all these problems that we address here, forget it. It's really just draw the fiber, it's without any precaution, you can have a higher impurities. Why we are using this shot fiber of borosilicate? Because they enhance the mechanical property of your ceramic. This is a different kind of application. And you have also this borosilicate fiber that you can use for textile also as to avoid all these thermal effects. This is another application for that. And you have also you have borosilicate fibers that you can match with carbon fiber to make this for the aerospace application.
First of all, thank you for your talk. It was very nice. Some weeks ago, I found a patent of some guys that combined transversal holes with longitudinal holes in optical fibers. But I didn't find any published paper about that. By your experience, do you think that it is possible to produce this kind of fibers?
You mean transversal?
Radial holes. It was a patent idea, so.
In which patent? In which year?
I don't know, 2 years ago or something.
I haven't.
Because it could be very interesting for sensing to produce this kind of fact.
Do you mean radial holes by drilling holes in the side of the fiber?
Yes.
Yeah, I think this has been done by Cristiano.
Yeah.
Hasn't it? Yeah,
Cristiano Watermark.
No, this is radial. On the side of femtosecond lasers, so that
by drilling with the laser.
Yeah, that's right. With femtosecond lasers, that's been done. But it's Cristiano Dumont.
Cristiano, yeah.
He's been doing that at Mackenzie.
Yeah.
From Unica?
No. Mackenzie. Yeah, he and I thought you had done some work with him as well. Maybe I'm wrong, and Walter Margulis has been doing it as well. The way of accessing the core of the fiber through the side has been done now by several people.
Yeah.
I believe it's the Australian group has been doing it as well, Sydney, and in the UK at Southampton, and we will very soon be doing it.
Yeah.
Okay, thank you.
I wanted to mention that Eno is doing something like that. I believe they have a patent for drill, and they use it for flow cytometry. And there's a spin-off company, right?
You are right.
Yeah, I forget the name. I forget the name of the company, but there's a spin-off company based on a patent by Eno, and they use it to measure particles in flow streams.
Yeah, you are right. That's it. Yes. For cytometry application. David, you asked me at Quebec. You asked me in Quebec, not here.
In French?
In France.
I think it would be of common interest to discuss the MCDE technique and another complementary technique based on melting instead of vapor deposition for preform synthesis. Right? You showed this in the middle of your talk.
Yeah.
Can you comment on the advantages and the drawbacks of each technique, depending on the type of material that you want to transform into a preform?
Okay. Thanks, David. I forgot to mention that. It's question of time. They give me just 2 hours. It's 4 hours.
I know. That's why I'm asking now. Just 1 minute.
Okay. The first thing, if we would like to get low losses, remember I said vapor process, MCDE. If we are looking for low losses of fiber, it's an MCDE because using the technique of rotational process, we never get the low losses because we will start from the solid state, we melt the compound and we produce the glass. We have a lot of impurities. This is the first thing. The second major point, we will have problem of interface between core and cladding. Almost the best technology we are almost using will have defects between the core and cladding. And major part will have some bubbles inside the core during the preparation process. We have a lot of drawback from this technique. But this technique, it is the unique technique actually. Use it for preparing chloride glass fibers. We haven't another technique. And we need to survive with that. If one day we'll be able to produce fluoride glasses using MCVD technique, and I know Japanese in Ohoya Glass Corporation and other people are working hard on that. And I know another group in UK recently, we met him in Islam this year. They are working hardly on that also. In both fluoride glasses and also chalcogenide glasses. They want to go to the vapor deposition process because it's clear now. We never will reach the lower losses if we go just like this process. I answer your question?
Yes, thanks.
I just also comment on that. Very quick comment. Thanks. Thanks.
Younes, is it not true that sometimes you don't have a choice right now because of the material degradation problem? That if you do it by vapor, that you do degrade the material as well. Is that true? I mean, for example, chalcone lines.
Yeah.
How can you do them without them degrading or crystallizing or something in the vapor phase? Is that a possibility?
The answer is we can't do it yet. If we know how to do it, I will go to that. We start from recent work with Sydney and one of PhD students have been in Laval, and when we start using what we call soldier process, with the way to improve to get the success, just one compound. This is just one compound of all the huge different elements. We have been working just for one element, which works. But now, if we add the other element, what will happen? The student will tell you, Denise will tell you in 3 years. Hopefully, in 3 years we'll succeed. But believe me, in my opinion, we must work in this direction. Soldier or vapor processing the weight. Why vapor processing? Why with the chalcogenide you can start with some organometallic element, like this stuff from arsenic, and you can add it as gas, and the way you can produce. And the people like what is his name? Dan Dua, he's working this direction. SAMPA. Dan Dua is working this direction. Because I met him, I've been discussing that they got a lot of funding and they are putting the effort in the really gas process, H2S and some organometallic.
Thanks.
Yeah, you said I didn't do it.
Okay, any more questions? If not, thank you again.